Okay, so welcome back. Now in this video we're going to talk about an infinite sequence, and we're going to introduce vocabulary and definitions so that we can start with that and then build from there an idea of how to handle sequences, and then we'll talk about convergence and divergence, just like we did in when we're dealing with improper intervals. Okay, and we'll see how this also relates to improper intervals later on. But let's start with definitions. So what is an infinite sequence? An infinite sequence is nothing more than an ordered list of numbers that go on for infinity. Okay, so we can represent that ordered sequence as such. Where do I want to start? Okay. Oops. Okay, so here's an ordered list. Okay, and so this would be an example of a sequence. And so each one of these is called a term. Okay, so each A sub n, or in this case A sub 1 and so on, is called a term of the sequence. N is called the index variable for the sequence. Now, we can represent it this way, but more commonly we can represent the infinite sequence using this notation. Okay, so now again, this represents a sequence, an infinite sequence. As you can see, the index goes from n to 1 to infinity. Also realize the set braces. So this is a set of numbers, but it's an ordered set of numbers. That's the difference. Okay, so A sub n represents the form, okay, of the sequence. We'll get to that in a moment, but this is how we represent a sequence. Now, we can also represent it just without the indices, A sub n. So if we write it this way, it's assumed that it's going from 1 to infinity. Okay, so again, you can either write it this way or this way. So if there's no indices, it's always assumed that n equals 1 to infinity. Okay, now, how do we look at sequences? Well, let's take a look at an example. Okay, so let's look at this example here. Let me see. Okay. So, let's look at this. So this would represent A sub 1, A sub 2, A sub 3, and so on. Okay? And so what can we see that's going on with this sequence of numbers? Okay, so A sub 1 is 2, A sub 2 is 4, A sub 3 is 8. Okay, and so you can probably see the pattern already. In fact, we can write this as what? 2 to the first power, 2 to the second power, 2 to the third power, and then we can keep going. 2 to the fourth, 2 to the fifth. So it looks like this is powers of 2, right? So if this continues in like fashion, then how can we represent this? Well, we can represent this as what? 2. And it seems like the exponents match the indices. So let's write this infinite sequence as follows. Okay, or we could just write 2 to the n, right? So we can drop these and just write it 2 to the n. And so that's how we can represent it. Now, alternatively, we can describe the sequence in a different way. Since each term is twice the previous term, right? So each term is double the previous term, right? We can also define this in what we call a recursive manner. Okay? And so we can define this recursively by expressing the nth term a sub n in terms of the previous term a sub n minus 1. Okay? So what we can do is, in this case, we can define this sequence recursively by saying a sub 1 equals 2, and then a sub 2 equals what? A sub 1, what? Times 2, and then a sub 3 equals what? A sub 2 times 2. So this would be equal to 4, and this would be equal to 8. And so we could write this, the nth term, we could go a sub n equals a sub n minus 1 times 2 to the n minus 1. Right? Because this is equal to 2 times 2, right? So it's n minus 1. And this would be equal to 4. Hold on. No, it'd just be a sub n minus 2. Sorry, I'm getting ahead of myself. There we go. And this would be equal to 8 times 2. Okay, and so that's another way we can do that. Now we could also write this as a specific explicit formula too, okay, that we're going to see as well. Okay, so now, so what do we call this? We call this a recurrence relationship. Okay, so this is called a recurrence relationship. When we write it as a term, the next term in terms of the previous term, okay? But sometimes we can have a recurrence relationship where we're including the previous two terms. For example, the Fibonacci sequence, or Fibonacci series, or sequence of numbers. The Fibonacci sequence behaves very similarly as a sequence of numbers, where we get 1, 1, 2, 3, 5, 8, 13, and so on. And so this number here, we start with these two, a sub 1 and a sub 2, and then a sub 3 is these two summed together, and then a sub 4 is these two summed together, and so on. So it's the sum of the previous two terms, okay? So that's another thing keep in mind. Now, we can also define a sequence that does not start at n equals 1. Okay, so the index doesn't have to start at 1. It could start at 2. We can also define it to start at 0. Okay? Oops. So this one here. Okay, so let's do this. Okay, that's it. So next video, I'm going to introduce the definition. So we're going to introduce the definition of an infinite sequence, and then we'll go on and do some examples of writing infinite sequences using the recurrence relationship and also getting explicit formulas that represent a sub n for any n. See you then.